Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this course on electrical technology. This is the first course on electrical technology. So, in this course I will introduce you basically to the basics of electrical engineering, which is giving you an introduction of why we have a 3-phase AC system, what is a 3-phase AC system. Then I will also introduce you to few of power apparatus, that is devices or power apparatus, which are I'll let me list them. So I will start with why do we use electrical systems. I mean, if you look at it, the complete mankind is now today dependent upon use of electrical energy. It's almost as prerequisite like food, water, air. The importance of electrical energy is at the same level. Even your communication systems that you use, the mobile devices, are also powered by basically electricity only. And if you look forward on what's happening in the automobile sector, what's happening on the road, then you find that electrical vehicles are now becoming more and more important because they cut down on pollution, they are non-polluting, they don't emit emissions on the road, and they are silent, and they are light, and they give you very good power drive, so to say, instead of earlier engines which we were having diesel or petrol or IC engines, as they are called, internal combustion engines. If you step back a bit, you would notice that this revolution on the electric traction, that is railway trains, has already happened, and most of the electric traction is actually is done using electric motors. The railway engines are essentially electric motors, and that same revolution has now sort of started appearing on the roads. If you look within your home, then also you would find that this revolution of using electrical technology is continuously marching, progressing within your house also. So, for example, of course, the lights that you use for such a long time, since you were born, much before that, is completely electricity based. Water heating, especially if you look at geysers in your bathrooms, they are based upon electricity. They consume significant amount of electricity. Then you have fans which are based upon electricity, and over last few decades, maybe a decade or two, if you look at it, air conditioners usage has also gone up significantly. They are also driven by electricity. They are also driven by electricity. If you get inside kitchen of your house, you would find mixer, for example, grinder. And for cooking, usually we were using LPG, liquid petroleum gas, for cooking, but there is more and more emphasis on that also being replaced by electric heating, by electric heating, induction heating plates. As you see, you have rice cookers which are based upon electricity. Then you have microwaves which you regularly use for heating, and oven which is based upon electricity. So, it goes without saying that it goes without saying that this civilization, the mankind, essentially depends upon electricity. And basically, why does it depend upon electricity? Because it can be, one, generated conveniently, it can be generated conveniently. So, that there are many good electrical generating methods, electricity generating methods. Two, it can be consumed conveniently. So, you can consume it also very conveniently. I just listed to you so many applications which are basically converting electrical energy to different things. They are converting electrical energy to different things. Like I talked of heating applications, I talked of lighting, I talked of motors. Basically, they do, what do motors do? They do mechanical work. So, these are three main category of applications that I talked of. Now, something, first of all, if you look at it, electricity as such is not existing in a natural form in your surroundings. You know, you don't like, you can go and pick up a set of leaves, or you can go into a pond and pick up some water, or air is just freely available to you. So, like that you can't go and pick up a glass of electricity, so to say. You of course can buy a battery, of course you can go and buy a battery which has electrical energy in some form or other stored inside it, and it will give you some joules of energy at certain voltage, and afterwards it will discharge, that is why you have to charge your mobiles or something. So, what I mean to say is, there is fourth category of application here that I am talking of, and that is storage. So, you can store also, it is not like small scale storage in terms of battery is very predominant. Large scale storage has, so to say, started picking up now. I mean, there are now lot of large scale storage applications also coming up, but you can store also electricity, but naturally it is not lying around. So, therefore, what I mean to say is, naturally you will see that you can easily create mechanical energy, you can easily create heat energy, and you have enough amount of sunlight available, coming the sunshine which is available. So, this is light energy, and therefore, the first step that we have to do is any of these forms of energy we have to convert it into electrical energy. This a device which does this is called typically called a generator, and the most common way of converting mechanical energy, creating mechanical energy is sometimes even mechanical energy is not like freely available to you. You can see lot of things moving, but none around you is actually moving permanently as if it is a source of mechanical energy. So, even the mechanical energy also you have to create. So, the traditional electrical generators first of all what they did is they created steam, that is burnt coal or gas. So, it could be a gas generator or it could be a coal based generator. So, first of all you burn it, this creates significant heat energy. This in turn in a thermal generator, this in turn drives, boils or creates a high pressure steam, which is basically water is boiled and superheated, and superheated to high pressure steam, and then then what you do is in this, when this high pressure steam is created, then you actually that high pressure steam goes through a nozzle which creates a high velocity rotation of what is known as a turbine. So, this when this goes through high pressure steam, when it is released through a nozzle will create a very high velocity steam which is ejecting out, which impinges on the blades of a turbine, and then the turbine starts rotating at high speed. So, I will roughly explain it to you like this. Let us say I have, for the sake of simplicity, just a magnet here, so let us say that I have a magnet sitting here which is facing north and south, and imagine that this is connected from behind to this rotational equipment which is causing this magnet to rotate at a high speed. So, this magnet is rotating through a high speed, and this here, what I have got here, this is a iron core,
Why do I use iron core? I will have more of it later on, but basically I am using a iron core because iron is conducts, if I can use that word very roughly, magnetic fields very well. That means it puts very little opposition to creation of the magnetic field. So, I will have this kind of magnetic fields which are going through I will have these kind of magnetic fields which are going through this because of this magnet. There is here, what I have got here is a air gap, because something is rotating, something is fixed. So, whatever is rotating should not be brushing or touching the non-rotating part. So, therefore, magnetic field is set up here which is rotating in this particular case, and let us say that I have a winding here which I am showing by, let us say, it is actually not, it is here sitting somewhere here, which I am showing by A and A plus. A plus and rather A minus. So, this is the winding. So, the winding is, if you look at it, it is something like this. There is this conductor which is there in the magnetic field. This is a overhang which is coming out, then it comes back here. So, I have these two conductors which are coming here, and then again you could have something which comes out like this, goes back, and then again the conductor comes out, and so you could have many turns say n number of turns which are happening here. So, then there is a coil, and now you can see that this coil here, which this is the part which is there in the magnetic field, this part is there in the magnetic field, these overhangs are outside of the magnetic field. Now, when this magnet rotates, which is happening because of the rotational kinetic energy which has been created by heating by burning coal. So, that is the raw form of stored, that is actually energy storage. That coal is essentially stored energy which can be converted easily to a heat form, which then we created to boil water in the boiler, and then created high pressure steam which impinged on the turbine, which created a rotational kinetic energy. So, now this rotational kinetic energy, but the rotational kinetic on that, what was rotating, a magnet was housed. So, because the magnet was housed, so now this is rotating at a very high speed. So, if you look at our systems, you would realize that in India we have a 50 hertz system. So, that means whatever we see here in India, voltage waveform, that voltage waveform has a periodicity of plus minus 20 milliseconds. So, 20, rather than writing it, I will write it as plus minus nt, where n is an integer and t is 20 milliseconds, which is 20 into 10 to the power minus 3 seconds, which is 0.02 seconds, and the frequency is the reciprocal of time period. So, therefore, it is 1 by 20 into 10 to the power minus 3, which is 1000 by 20, which is 50, and its unit is hertz. So, you are getting a waveform, a periodic waveform with 20 millisecond time period, and incidentally that periodic waveform is a sinusoidal waveform like this. And t equal to 0, if you want to put t equal to 0 somewhere, you can conveniently place it anywhere here. There is, really speaking, we do not have any t equal to 0, we were born in a continuation of time, and we really do not know where our t equal to 0 is there, but for electrical engineering analysis we can conveniently place t equal to 0 here, and then whatever here is a positive time for us, and whatever is here is our negative time for us. So, this voltage waveform, which we have to see in this course as we proceed, we have to see in this course that this voltage waveform is actually a sinusoidal voltage waveform, which I can write it as sine of omega t plus phi, a sinusoidal voltage waveform, which I can write it as sine of omega t plus phi, where omega is 2 pi by t, which is equal to 2 pi of 1 f. If it is 50 hertz, then it is 100 pi, which is approximately 314 radians per second of speed. Worldwide, voltage waveforms that you get anywhere in your home or anywhere else are this sinusoidal, as it is called, AC waveforms. Actually, C stands for current. So, it is actually alternating current, as many places it is called, and the other thing is a DC waveform, which, like for example, you get in your batteries, AAA batteries or whatever, the direct current. But current is actually, there are really speaking there are no current sources that easily available. Just like I said that electrical energy does not appear naturally stored in the nature. Similarly, current sources are not that naturally available. What are available to you are basically voltage sources, and if you connect a resistor across it, if you connect a resistor across it, and this is a voltage source V of t, and this is a current which is flowing through I of t, then I of t is going to be equal to V of t by R, which is unit of voltage is volts and unit of current is amperes. So, and this is your, if this is just a plain resistor, then this is your Ohm's law. And just to recap, current is nothing but rate of change of charge. So, 1 ampere is nothing but equal to 1 coulomb of charge flowing at a rate through any point at a rate of 1 coulomb per second. That flow rate of charge is called as 1 ampere, and the voltage unit is actually as I said voltage unit is actually it is the potential, and its unit is volts. Now, DC, this AC is shown by this notation. you show AC by a sinusoid inside a circle, and even if you, for your polarity convention, even if you mark it as plus minus, even if you mark it as plus minus, remember that a voltage waveform is alternating. It is positive here, it is negative in this area, becomes positive again, and so on. And let us say if this is plus 1 volts, then though I have not drawn it to scale, this is actually minus 1 volts. So, the amplitude, the positive peak amplitude and the negative peak amplitude are going to be same, and if this is 20 milliseconds, then this is going to be half time period, which is 10 milliseconds. This is 0, then it is minus 10 milliseconds here and minus 20 milliseconds here, 30 milliseconds here, and so on. So, you have you have basically the plus minus is shown for writing Kirchhoff's current law, rather this is shown for writing Kirchhoff's voltage law, and the other law which has to be followed in electricity is the Kirchhoff's current law. Just to recap to you, let us say, just to recap for you the KCL and the KVL as I usually abbreviate it. If this is my circuit, let us say, and I have put a, just for the sake of I have taken a circuit here which is a RLC circuit. This is a resistive element, this is a inductive element, this is a capacitive element, and this is R2, let us say this is R3, and it has only one supply which is V of t, and I, for the sake of writing, write it as plus minus here. Then if I call current here as I1, let us say arbitrarily I write that the current which is flowing out here as I2 and the current which is flowing out here as I3, then what I can do is, what I can do is what I can do is, I can, let us call this as this node, this junction which is also called, let us call this as node A. Then Kirchhoff's current law says that current which is entering this node should be equal to current which is flowing out of this particular node, or in other words, minus of I2 minus of I3 should be equal to 0. That is to say that no charge is accumulated at the junction. So, in this case there is only one non-trivial node A which we have to write, and automatically it is clear to you that the same thing is valid here also, because the same current I1 should go back from here and the same current I3 should come back from here. So, the other one is other end node, it is anyway automatically valid. So, Kirchhoff's current law is a very fundamental law, and then any loop if you take, okay. So, let me take for example this particular loop. Arbitrarily, in this example there are 3 loops, this is 1, this is 2, and this is the third loop, does not matter. Any loop which if I take and if I write the voltage equations across that loop. So, let us say that this voltage drop is, I will show it for 1, this voltage drop is V R 1, this voltage drop is V L 1, this voltage drop is V R 2, this voltage drop is V L 2. Then if you trace this outer loop for example, if you trace this outer loop for example, you would see that starting from here a voltage rise, which I will take it as positive. So, voltage rise of V t is positive, and then afterwards by my marking convention everything is voltage drop. So, I will show it as negative, which is minus of V R 1, minus of V L 1, minus of V R 2, minus of V L 2, and then I am back to my original price. From here I had started voltage rise of V t, voltage drop of V R 1, voltage drop of V L 1, voltage drop of V R 2, voltage drop of V L 2, and I am back to the original point, and these wires obviously have 0 resistances. So, ideal wires. So, therefore, since you have come back to the original point, your energy is going to be, potential is going to be the same. So, therefore, whatever was the rise has to be compensated by the drop and you get this basically equation, which is nothing but the application of KVL. So, the point is KCL and KVL will be used throughout the course, but coming back to the earlier discussion, I said that we have voltage source which will be sinusoid, that is what is easily available. Even though we say alternating current, the current is actually only a derived quantity, it is basically it is only a derived quantity, it is the voltage that you get in your supply. So, if you look at your home for example, you have 230 volts coming at 50 hertz, this is called a single phase supply. So, that means actually that your voltage waveform that you see is of this particular type. I do not know the phase angle until I fix my reference axis, I do not know the phase angle, but this is a sinusoidal of this. This value that I am getting here as which you get as 230 volts is actually a root mean square value. So, if this is my waveform V of t, say sinus of time period 0 to t, V square of t dt divided by 1 by time period and square root of this is what is the root mean square value. So, root, look at it, read it backwards, root mean square, this is why it's abbreviated as RMS, and this is what for a sinusoidal quantity, we will see this again later some point of time. If it has an amplitude of Vm, then Vrms would be Vm by root 2. So, that is why whatever in your electrical homes, whatever supply voltages that you read, AC equipment, whatever rating that you read, all of that is basically a RMS value. And so, if you want to write the corresponding sinusoid, you will have to use 230 for example root 2 sine of 100 pi, which is 2 pi f, f is 50. So, 100 pi t times of phi. Now, if you are for example, in USA for example, you would have a 110 volt supply there at home and 60 hertz frequency, it is different. Most of the world is on 50 hertz, but North America for example is on 60 hertz supply, then this will be 120 pi of t plus phi. So, the electrical engineering will not change really speaking, but the voltages and the frequencies which are standardized are changing. One more thing that I want to introduce to you is a term called 3-phase supply. So, these are some of the things that you are every day all your life you have been coming across, but it is only now today that we have got time to discuss what this means. So, 3-phase supply means usually shown by A phase, B phase and C phase supply. So, usually shown as A phase, B phase and C phase. So, if this is let us say for the sake of discussion taken to be sine of 100 pi of t, then this one is the B phase supply is 100 pi of t minus 2 pi by 3 radians, and the C phase supply is 100 pi of t minus of 4 pi by 3 radians, and 2 pi by 3 radians is 120 degrees, 4 pi by 3 radians will be 240 degrees lag. So, therefore, this can be also written as 230 root 3 sine of 100 pi t plus 2 pi by 3, because in a circle, in a circle like this, let us say this is the 0 direction. If I look, let us say this is minus of, so this is minus of 120 degrees, and then I go further back. So, if this represents A phase, this represents B phase, this represents C phase, then this lags another 120 degrees. So, this becomes minus of 240 degrees, but this is going to be same as plus of 120 degrees, which is 2 pi by 3 radians, which is plus 2 pi by 3 radians. So, you usually have a 3-phase supply like this in your home. Many of your equipment will be like, for example, a geyser, a bulb would be on, for example, on a single phase supply, but there could be equipment, for example, your air conditioner, your refrigerator, which would be on a 3-phase supply. So, usually when you require more power, a 3-phase device is many times created. When you are dealing with small amount of power, usually a single phase device suffices, and your utility or people will tell you that your supply is 400 volts 3-phase or 230 volts single phase. There is a relationship between these numbers also. This 230 volts into root 3, which we will also see in this course where it comes from, gives you this 400 volts. So, and this is usually called as a line to line supply. So, if you look at your if you look at your, for example, a three phase connection, for example, there would be 3 terminals for A, B and C, and usually a neutral which will be grounded somewhere, Why will it be grounded for somewhere? it will be grounded for safety. Electrical equipment is a dangerous piece of equipment. It can your body itself works on significantly on electrical signals. Your heart, for example, also works on electrical signals. Your nerves require electrical stimulus, and those are very micro or minute level of electrical signals which are flowing there. So, if you by mistake touch a supply like what we have at home, 230 volts or something, then the amount of current which can flow through you, which can flow through you, you should never touch it. Please, I mean, I am not trying to say by mistake also if it happens, then that can be life threatening. So, therefore, whatever thing that you come in contact with, in an electrical apparatus, has to be properly insulated so that you will not really come in contact with that voltage. So, insulation is basically providing a high resistance kind of a thing which will not allow any current to flow. The voltage by itself is not dangerous, but what is dangerous is the current which correspondingly flows. The V by R which I had shown here, this V by R is what is dangerous. So, whenever you talk of insulation, then the insulation is a very high piece of resistance that is there in when you talk of insulation. The other thing is, like refrigerator or whatever, when you touch there is a surface. That surface also should not be having any charge or voltage. So, therefore, all electrical equipments are basically grounded. By grounded means earth is taken to be a surface which can take any amount of charge, or it can give you any amount of charge without changing its potential, because with respect to earth, whatever we are doing, whatever big scale we are doing is still like drops of water in an ocean. The earth is your ocean, and whatever we are dealing with, our voltages are basically drops there. That will not alter, that those drops going into ocean or those drops coming out of ocean are not going to alter in any case the ocean. So, the earth potential is taken as a standard or reference, and that we call that earth potential we call as 0 volts. Now, since we are standing on the earth's surface, we are actually already at the 0 volts. Now, if you properly ground your electrical equipments, then wherever you come in touch with, whatever are the exposed parts of it, whether it is a motor, whether it is a geyser, whatever it is, they will also should be at 0 potential, and that will be achieved if that P thing is grounded. You are standing here, you are also so grounded. So, when you touch, no current will flow. So, grounding is very important for safety, and we will probably hopefully get more time to talk about it later on. Now, before I close this lecture, I just want to come back to that generator that I was talking to you about. I said that you rotate this at a high speed. When you rotate it at high speed, what happens is that the flux which is connected with this right now, if you look at it, it is at the peak value of flux. When this will rotate and come at a position somewhere here, when it will rotate and come at some position which is here, then the flux which is associated with this coil AA plus, to which finally you have connected a resistor or whatever your load. So, that will turn out to be 0. This is I am plotting the flux which is linking this coil, and then when it rotates and comes back at the other way round, the north coming here and the south going here, the flux will reach its negative maximum value and then again come back to 0. And if the machine keeps rotating, this thing is going to keep on happening, this is going to keep on happening ad infinitum. So, therefore, the flux waveform in this particular case is going to be phi of t, phi m cos of omega t, where omega is 2 pi by t equal to 2 pi f radians per second, which in India is 100 pi radians per second. Now, by Faraday's law, if there are n turns and a coil connected to it is experiencing a rate of change of flux which is given by d phi by dt, then the voltage which is going to be induced in it, E of t, will be d of dt phi m cos of omega of t, and phi m and omega are constants. So, I will get minus omega m phi m sine of omega of t. So, I am sorry, derivative of cos is minus sine. So, I will get n phi m sine of omega of t, and this shows that the induced voltage is a sinusoid. Now, you know why it is a sinusoid. I will have later on a full lecture on why this flux waveform will look like a cosine wave. This I will explain to you much later. If you are uncomfortable with it looking like a cosine wave, you can for time being think of it as like this also. This is north, this is south, this is the rotation or theta, which is the angle which is taking place, and this is the flux of time. This is one way you could start by thinking of it like a periodic waveform like this, but by construction and by some analysis we will finally bring it to a cosine kind of a waveform. Now, this becomes your Vm, this becomes your Vt, and this becomes your peak voltage, and the RMS value, which is what usually you are given 2 pi f omega n phi m, the peak value, divided by root 2, this is usually 4.44 f n phi m, is the Vrms value that you will get. Now, the last thing, and then I am stopping this lecture. Why do we have a 3-phase system? Rather, what is a 3-phase system? Why we will come to later on. Now, if I just place one coil here like this, actually I am not using this stator really area or surface effectively. So, suppose I 120 degree behind, I place a winding like this, and the direction of rotation is always in electrical engineering, the standard direction is anti-clockwise. So, the omega is like this, and I place here 120 degrees later a B plus B minus winding, and then another 120 degrees later I place a C plus C minus winding, then you can see that by symmetry and the rotation you can see that whatever happens electrically to A plus A minus winding, the same thing will happen to B plus B minus winding after a time period of T by 3, and whatever happens to C plus and C minus winding will be exactly same as what was happening to the A phase winding, but with a delay of 2 T by 3, and then again another T by 3 delay, and you are back to the A phase winding, which is 3 T by 3, which is basically T. So, if you had to use your stator surface more properly, you had set up 3 sets of windings like this, then you would get basically a 3 phase supply, which is what I have shown here. Now you may ask why not 5 phase, why not 6 phase? You can actually set up like this any number of phases, but over a period of time frequency 50 hertz in India is standard, supply 3 phase is standard, whole over the world also 3 phase supply has become standard. Whatever benefits we wanted, we can get it from 3 phase. I will explain those benefits later on, and that is why we have traditionally a 3 phase AC system. Nowadays, because of PV picking up and PV generating basically a DC voltage or so, you are also getting DC supplies are also coming back, and computer is one device which I did not really talk about, electronics I did not talk about at all, which is usually driven by DC. So, DC voltage supplies are also making a comeback, but predominantly the system continues to remain as a AC system, and this predominance we will discuss again in more detail in the next class. We will take a break here. Thank you.